the sorry for the delay in starting. We needed the introduction from the Abali Center. This is an interactive class. Feel free to ask questions on chat or anywhere else, or just speak up at any time. So welcome again to Introduction to Deep Learning. This is the Spring 2023 version. So wait a minute. Yeah. Hopefully, by now you've all seen the logistics post on Piazza. We have a logistics lecture. We have a couple of posts. Hopefully, you've also seen the course website, deeplearning.cs.cmu.edu. We deal with everything through this website. So please do go there and take a look at it. Everything from course objectives, logistics, quiz, homework policies, grading policies, everything is on the website. And you need to familiarize yourself with this information so that you are clear about exactly what is going to be expected of you in the next 3.5 months. Also, by now you should already have signed on to Piazza. You should have verified that you have access to Canvas and Autolab. You should have Amazon, the AWS account set up, and also tested out Google Colab. We have a post about forming study groups. We highly recommend that you form study groups. If you cannot form a study group of your own, then we will form them for you, and that will be done by the end of the course deadline. But please do sign up for the study groups because it's going to be very important to have teammates to work with. Our course philosophy is simple. In our ideal world, every one of you gets an A. And we actually work very hard to make this happen every single semester. In each of the past, first, I want it to be very clear. This is an immensely difficult course. It's not easy. On the other hand, in each of the past 5 semesters, I think, 70% of the students have got some version of an A, and 85% of students have got, or sometimes 90% of students have got some version of B or an A. So that's mostly on you, but also on my TAs and myself. We work very hard to make sure that everybody gets the subject because we want to teach. Make sure you use all your available resources. We have TAs, we have study groups. Each study group is going to have TA mentors. We encourage collaboration. We hold about 40 office hours every week. You can always reach out to me. You can just email me or just walk into my office if I'm free. You can talk to your classmates and friends. Use all the resources available to you. And again, the course is tough. It will be a lot of work. If you feel you're under stress, if you're unable to perform, always do not just let this fester. Do not let this settle to the background. The longer you wait, the worse it will get for you. Reach out to your TA mentor or to me, and we'll try to get you sorted out. We'll be holding hackathons on Saturdays. The room is not yet decided. We should have an idea soon. And hackathons are where we will sort of bring you in, and hopefully you come in with your study group. You get to work on homework assignments and ask questions. So we will be posting the time for hackathons, time and room. We haven't got the room yet. You're allowed to talk about the lectures, allowed to talk about the homeworks. You're allowed to talk about the quizzes with your friends, with your study groups, with your classmates. The only requirement that we have for you is that when you actually answer the quizzes, you do this by yourself. You don't just sit and answer these in a group. You don't get the answers, you don't copy, basically. The same thing with homeworks. You may discuss your homeworks. You may have your friends debug your code. You can debug your own code, but the code that is finally submitted must be yours. Or the code that finally runs must be yours because you're here to learn. You're not here to show me that your classmate learned. So we need you to code. Also, all of these, trying to get help and in meeting with students can be done in the hackathon rooms. It's also a great place to find teammates to group up with for study groups. So try to be there at the hackathons. We have 3 course objectives. First, we want you to understand some of the theory behind neural networks. We want you to be able to build your own neural network components and tools. And we want you to be able to work on large scale problems. So by the time you're done with this course, at some level, we hope that you will be prepared for the big world in terms of being ready to work with deep learning. So about the first course objective, we want you to be able to understand the what, the why, and the how behind deep neural networks. So this is both the math and some of the history. And also, knowing the theory behind neural networks will help you contextualize what it means to build your own network or world, work on large-scale problems. And some of the focus on the theory behind neural networks is because this is also going to be something that you will need for research for your grad school. And it also relates to questions that you're likely to be asked in job interviews. If you've been following the course well and kept up with things, then at the end of the course, if someone in a job interview asks you a question and doesn't like your answer, it means that person is wrong, not you. Now, we want you to be able to build your own neural network components. You're going to be working on several homeworks, as you already know. And the part one, each homework has 2 parts and some bonus problems occasionally. And the part ones and the bonus problems are where we teach you to build your own toolkit. So if you're stuck in the wild without a ready-made toolkit, you're not going to be lost. And of course, the part twos of your homeworks teach you to work on large-scale real-life problems where you actually work on state-of-art tasks and try to achieve state-of-art results, which you will, believe me. Even though you may have come in cold, at the end of the semester, many of you would have actually achieved state-of-art results on state-of-art tasks. And of course, for those who are in 785, there's a course project. Course projects may have to do with the theory about building systems or working on some large-scale problems. My lecture style is verbose. Lots of visualization, so I use many slides. It is not at all surprising to find me go through 260 slides in an 80-minute lecture, but mostly because it has a lot of animation. Given a choice between deriving an equation symbolically and explaining it with 30 slides of pictures, I'm going to do the pictures. If you don't like that style, then this is not the class for you. I've had students complain in the past. I don't want you to be surprised by how the class is conducted. So this is advance notice. We want you to participate. So we're going to use in-class polls, both in the Zoom lectures and in-class lectures. We will periodically post quizzes or polls. And these are going to be posted on Piazza, except if, of course, if the lecture is on Zoom, in which case these are going to be Zoom polls. And we want you to respond to these polls. We're not scoring you on correctness, but by responding, you're showing that you're paying attention. Now, everyone is expected to come to class, either in person or watch over Zoom. And so that's how, through these polls, we're going to get an idea of your class participation. Some people have conflicts, course conflicts, others are in bad time zones. Such students have actually written to me and they have explicit permission from me to not be in class and to watch the videos later. That general permission doesn't extend to the entire class. This is an interactive class. We like questions. And my philosophy is that, and my TA's philosophy is that there's no such thing as a silly, wrong, or embarrassing question. It doesn't matter what the question is. If you have a question, you must ask it because you're all very smart students, very smart kids. And if you have a question, regardless of what you think about it, the odds are that out of the 270 people in class, there's at least one more person, if not a dozen other people who have the same question and have maybe not opened up and asked the question. So if you have a question, then never ever feel embarrassed. There's no such thing as a silly or foolish or embarrassing question. Every question is valid. Please ask, and we will try our best to answer. And also, we're going to try different tactics to try to encourage you to interact. So, Sometimes we just give out numbers to everybody and we call out numbers to answer questions, but we may try other things, but we want you to participate. Also, this is what I call a dumb classroom. We want you to keep all of your other smart devices, your phones, your iPads, whatever, shut, except to answer polls, or if you're following the lecture slides along, or to take notes. But we do not expect your phones to ring in class. We do not expect you to go on Facebook or begin whatever, letting your attention wander and going off and doing other things. You're not allowed to work on homeworks from other classes, to be reading up something else when you're in class. You're supposed to be focused on the class. And if we find you doing something else, then I may ask you to leave the room. And last but not the least, for those who haven't seen me, I'm physically handicapped. So sometimes my gestures are going to be odd. I have strange mannerisms. I cannot do some things. I can't raise my arms. I may ask my TAs to clip on my microphone if it falls off. I carry light plastic devices to point. And some students in the past have found this to be offensive. So I'm letting you know in advance that this is how it's going to be. If you find it offensive, I cannot help it. So that problem is yours. I'll pause a minute here for questions. Any questions? Anybody? No. All right, so let me begin. First, I'm going to go through a lot of slides, but the slide deck itself contains many more slides than what I will be going through. And so these hidden slides are not going to be shown during the lecture, but will feature in your weekly quiz. So please be sure to go through the slides again after the class to make sure that you're prepared for the quiz at the end of the week. So today we're just going to, it's going to be a light class. It's a brief history on neural networks, on connectionism, on early models and their limitations, and we'll introduce modern neural networks and what they can compute. So one of the reasons you're in this class is neural networks have become the main approach to AI. They've been successfully applied to various pattern recognition, prediction, and analysis problems. And in pretty much every problem that they have been applied to, they have established the state of the art and exceeded previous benchmarks by humongous margins. And sometimes they've solved problems that you couldn't solve using earlier machine learning methods. So for example, speech recognition. We've been working on speech recognition since the 1950s. And yet in 2015, if you used the best speech recognizers around, if you went to Siri or the Android recognizer, very often there was very little relationship between what you said and what the system recognized. And then in 2016, for the first time, we had this report that Microsoft AI outperformed human beings on a speech recognition task on the switchboard corpus. It was the first time that machines beat humans on any task of speech recognition, and it was because they were using neural networks. Now, of course, the latest speech recognition systems are in fact much better than humans on most tasks. Same thing with machine translation. In 2015, if you went on Google Translate, which was the best system at that time, and translated something from English to Spanish, then took the Spanish and translated it back to English, what went in and what came out would be completely different. In fact, we used to sort of use that for fun, just to see how bizarre the output could be. And then in late 2016, suddenly, overnight, the systems became useful. And that's because Google Translate suddenly switched to using neural network-based machine translation systems. These days, of course, machine translation systems are so good that even professional translators will first put their translation through Google Translate or something similar, and then just correct it rather than trying to do it from scratch. And for the layperson, you're probably better off going into Google Translate rather than trying to translate things yourself. That's how good it has become. Similarly, tasks like image segmentation. Here's a very complicated picture. And every object in this picture has been detected, segmented out, and labeled. And this has been performed by a neural network. 2016 again is when this began. Before that, performance of this kind was not even imaginable. Or games. So I just sort of keep coming back to this date of 2016 because that's when things really took an uptick. So for the longest time, it was thought that the real limit of artificial intelligence, how we would know when a machine became intelligent, was when it could begin playing and outsmarting human beings on so-called intelligence games. And the first game that we considered was chess. But then by 1996, we already had chess games that could beat a grandmaster. And by 2000, chess games had become so good that no human grandmaster has ever beaten the best chess games around. So does anybody remember where the first chess game that beat a grandmaster was built? Anyone? CMU. So that was actually a PhD thesis in 1989. That was what we call deep thought. Victor Anantharaman and this other person whose name I forget. And both of them then went to IBM and built Deep Blue, which beat Garry Kasparov. Anyway, we got past chess, but the next challenge was considered to be Go, because in chess there are something like 10 raised to 120 states, but Go has 10 raised to 180 states. And we thought it's too complex for computers to handle. It needed humans. And then in 2016, of course, we had AlphaGo, which beat the then human champion. And now you have computer, deep neural network based games, which can start from scratch with no idea of even the rules of the game and begin to learn playing the games. And within half an hour or so, or a few hours, it can become a world champion just by playing against itself. That's how good it has become. Similarly, here's another thing. These are all images which have been captioned. You can see the captions at the bottom of the image. These captions were generated by neural network. And if you actually read the captions, they are very, very appropriate. Like this one on the right, boy is doing a backflip on a wakeboard. Or man in black shirt is playing a guitar. So these captions look like something a human might have given these images. And this result is from 2016. Now, just prior to this, the idea that a machine could automatically look at an image and describe it was unthinkable. And then suddenly, overnight, we were able to do it. And of course, the latest machines can write you entire stories around an image or a collection of images. We've seen that. And once again, this was made possible by neural networks. And so here we are, the latest. DALL-E can draw anything for you. ChatGPT can, here I asked ChatGPT to tell me the story of Perseus and Andromeda in iambic pentameter. And it didn't quite get the iambic pentameter, but it did get the whole thing in verse. So it's become, I would say that if you were conversing with ChatGPT, you'd probably find it to be more intelligent than most people you would meet on the street. So, and this has also been made possible by neural networks. And many more things, like from art to astronomy to healthcare to predicting stock markets, we're using neural networks everywhere. So clearly, we need to be learning about these things. This is the state of the art, right? But then, that's all very fine. Here's what they do. But what are these neural networks? That's what we're here to learn, right? And from our perspective, a neural network is just this box which performs some tasks. If it were performing speech recognition, the neural network is a box which takes in a voice signal and outputs a transcription. If it were performing image captioning, it's a box that takes in an image and outputs a text caption. Or it takes in a game state and predicts the next game state, and so on. But what's in these boxes? To get an idea, let's start with the root of it all. Every one of these tasks that I've been speaking about, whether it be recognizing speech or captioning images or playing games. These are all, basically brain-powered tasks, human tasks, where when we perform it, our ability to perform these tasks is powered by the human brain. So maybe we should begin by studying the human brain. How does it do what it does? Or even before that, what does it even mean? Obviously, what the human brain does is to think. So what does it even mean to think? What does it mean to be able to operate in the manner of a human being? Now, here are all the things a human can do. A human can learn. A human can solve problems. A human can recognize patterns, create, cogitate. You can just be having a shower, doing absolutely nothing, and you get a brilliant idea. So you're able to generate new ideas without even apparent external stimulus. So we have all of these very amazing abilities, which are very worthy of emulation. But then to emulate them, we need to know how humans work. And this question of how humans work has been with us for a very long time. The problem is, if the brain was simple enough to be understood, as Marvin Minsky says, we would be too simple to understand it. Regardless, that hasn't stopped us from trying. And so we do try. And we've been trying for thousands of years, in fact. The earliest models for how human cognition works goes back to 400 BC and earlier. So the first model that was proposed was by Plato. It was called associationism. So does anybody recognize this picture? This one? Has anyone seen this painting? It's very quiet. I'm guessing nobody has. This was the School of Athens. It's a painting by Raphael. And it shows pretty much all of the major scientists through history at the time when this painting was painted. So you have Socrates, you have Aristotle, you have various others out here. So anyway, these people came up with this original idea of associationism. And the idea was that humans learn through association. And this was the primary hypothesis for how the human brain worked for almost 2,300 years, through Plato and David Hume in the 1800s, Ivan Pavlov in the early 1900s. So what are these associations? Now, we all know what associations are. For example, consider lightning. Lightning, in your world, you will always observe it's generally followed by thunder. So after making several such observations, you might form a temporal association between lightning and thunder. So then, at some other point of time, having thus formed an association, you could see some lightning and say, hey, here's a bolt of lightning. And you expect that you're going to hear thunder. Or you could hear some thunder and you're going to infer that lightning must have struck because lightning is usually followed by thunder. So you formed an association. And this idea that associations between concepts are how things can be explained or predictions can be made, which are all key components of cognition, this still holds. Most machine learning still works on the principle of association. But then that still doesn't explain the brain. This explains what is happening. Where are the associations stored and how are they stored? For this, we have to go back and look at the brain. And by the mid-1800s, we sort of knew that the brain was a mass of interconnected cells, which were eventually identified later as neurons. And so within the brain, what you have is billions and billions of such cells, such neurons, and each neuron connects and has many neurons connecting into it, and each neuron in turn connects out to many neurons, and the entire brain as a network of such neurons. So the first person who actually thought about this and came up with a model based on the fact that the brain is a mass of connections between neurons was this guy called Alexander Bain. He was a philosopher, psychologist, mathematician, logician, linguist, and a professor. And back in his times, this was the late 1800s, being a professor was a big deal. It's not like today where anybody can be a professor. So in 1873, he wrote this book called Mind and Body. And he came up with the idea that the information that the brain stores is not in the cells, but actually in the connections, in the manner in which the neurons connect to one another. And he even came up with mathematical models for it. He said neurons excite and stimulate one another. And he showed how a connection, a network connection of neurons can end up producing different outputs for different inputs. Now, this seems like a very obvious thing to us these days, but in 1873, this was not so obvious. So here's one of his models. Here you have 3 inputs and 3 outputs. If A and B are high, let's assume all the inputs are binary, 1 or 0. If A and B are on, X turns on. If A and C turns on, Z turns on. If B and C turn on, Y turn on. So depending on the input combinations, on the input, the output changes. You can even have networks where you account for intensities. So different intensities of input can result in different outputs. Here, for example, X adds 2 copies of A, the input. Y adds 3 copies of the input. So a low intensity input would only excite Y, but a high intensity input would excite both X and Y. So these are, in fact, the earliest neural networks. And this was in 1873. So believe it or not, neural networks have been around for 150 years because it's now 2023. That's how long these things have been around. And even back in 1873, not only did we have the idea of such circuits, Alex Bain even proposed a learning mechanism. He said, when 2 impressions concur or closely succeed one another, the nerve currents find some bridge or place of continuity, better or worse, according to the abundance of nerve matter available for the transition. The words may seem complex, but it basically predicts what is called Hebbian learning, a concept that we still use. And he predicted this almost 75 years before Donald Hebb, who came up with this idea. So it was a brilliant insight. The problem was that in Bain's time, all of these ideas which we just take for granted today, they were considered very controversial. And as Bertrand Russell says, the fundamental cause of the trouble is that in the modern world, the stupid are cocksure while the intelligent are full of doubt. And so in 1873, Bain postulated that you need 1 million neurons and maybe 5 billion connections to be able to store 200,000 concepts, which he called acquisitions. Then in 10 years, he thought about it in the face of a lot of criticism, mind you. So he was sort of encouraged to think negatively by all the flack he faced. And he worried that he had not taken into account all the partially formed associations. So it's not as if these concepts and associations are just born fully formed in your brain. They must be gathered. And so at any time, you would have some partially formed associations. And so in order to account for those, you need a great many more neurons than just 1 million neurons. And so by the end of his life in 1903, he decided that his idea was foolish. Your brain just isn't large enough to store all of that stuff. We need too many neurons and too many connections. And he actually recanted. He apologized for his work. But then he was right the first time around, and he was wrong when he recanted. It turns out that the brain is fully capable of learning and storing more than what he thought it could. because the human brain actually has something like 80 billion neurons and 100 trillion connections, orders of magnitude more than what Tabane thought they were, and more than sufficient to store everything that we need and more. So today's idea is that the brain is a connectionist machine. Neurons connect to one another. The processing capacity of the brain is a function of the connections, how the neurons connect to one another. And so modern connectionist machines emulate this structure, the structure of the brain. So here's what a connectionist machine looks like. A connectionist machine is a network of processing elements, and all world knowledge is stored in the connections between the elements. And so this differs fundamentally from the standard computer that we currently use. Does anyone know what kind of architecture your modern processor has? Anybody? I don't see anyone replying, so I'll wait. That's a von Neumann architecture. So what is a von Neumann architecture, Vinay?
Yeah, so it has a specific set of programs, and the memory is different from the processing unit. So basically, the way it differs from neural nets would be in the mannerism in which it, accesses the data and processes it effectively.
So a von Neumann machine, or what's called a Princeton machine, is actually what we use in your machines, where you have a processing unit and the memory is separate from the processing unit, and the programs and data are stored in the memory. So if you want the processor to do something different, something new, all you have to do is to change the program in the memory, and now the processor will do something new, which is why you can have one little handheld device and it can do so many different things, because each time you wanted to perform a different task, you just load a different program from the memory. On the other hand, in a connectionist machine, the program is the machine. The manner in which the units are connected to one another is the program. So as a result, and it's also the memory. So as a result, if you want the machine to do something different, something new, you have to build the entire machine anew, which is why we don't actually build connectionist machines. We emulate connectionist machines on von Neumann architecture machines. And so the story so far is that neural network-based AI has taken over most AI tasks. Neural networks originally began as computational models of the brain, or more generally as models of cognition. The earliest models of cognition was based on associationism. The more recent model is connectionist, where neurons connect to neurons, and the workings of the brain are encoded in these connections. And current neural network models are connectionist machines. So we have our first poll. Let me release poll number 1. Wait, I've got to launch poll 1. Hang on. And all of you must be seeing the polls on your screen. You have 45 seconds for the poll. There are 2 questions. So Ryan, you may have to, I'm not sure why you can't see the poll. There are lots of people who are answering the polls. We'll have to figure this out. Okay. All right. Okay, I'm stopping the poll here. Does anybody want to answer the first question? B, the second one. The second one is, okay, how many connections? Yes, the first person that proposed connectionism was Alex Bain. The number of connections that exist between neurons in the brain is 100 trillion. And this number actually begins to bear greater relevance today than it ever did. So I assume every one of you has heard of ChatGPT. So ChatGPT is this amazing new AI that's blowing everybody's mind these days. It has 175 billion connections. And the next version of it, which is GPT-4, which is coming out shortly, is going to have 1 trillion connections. At 1 trillion connections, it still has an order of 2 orders of magnitude fewer parameters than the human brain. And that's how smart it gets. So by the time it gets to 100 trillion connections, of course, it's going to be, our electronic versions are going to be more efficient than our brain itself, which has to perform other tasks. So assume that at least from an operational perspective, it's going to be at least as smart as us, right? So none of them have 100 trillion connections. They're still much closer than to one, much lesser than 1 trillion. How do you emulate connectionist machines with the von Neumann machines? You write a program for it. That's what you do by emulating it. And so here, those are the answers. So getting back, connectionist machines are networks of processing elements where all world knowledge is stored in the connections between these elements. But what are these individual elements? Now, for that, we go back again to the human brain. The individual elements in the human brain are neurons. And a neuron is composed like this. It has a head, which is called the soma. The head has many little incoming tendrils, which are the dendrites through which the connections from the other neurons come into this neuron. When the total signal from all of these connections exceeds some threshold, then the neuron fires. And then the firing of the neuron goes down this long leg called the axon to other neurons. And this axon is protected by something called the myelin sheath, which is made of fat or glial cells. And in fact, it turns out that having this fat is extremely crucial. The more fat you have in your brain, the smarter you are. And they actually studied Einstein's brain to find out how it differed from other people's brains. He had the same number of neurons as pretty much other people, pretty much the same number of neurons as other people, but he had a lot more fat. And so those protect these connections, and then that make him smarter. And so it's actually, being called a fathead is assumed to be an insult. It's not. Being a fathead is actually a compliment. Anyway, so the first people to come up with a computational model for this were these guys, McCullough and Pitts. Warren, McCullough, so the speed of signaling. What do you mean by that question, Nika? So the myelin sheath over here protects this long leg. If the myelin sheath is damaged, that long leg gets damaged and the signals cannot travel. So these little orange blobs over here, that's what make your brain function. The more of it you have, the better your brain functions. Anyway, so here are these two guys. Warren McCullough was a neurophysiologist in the University of Chicago. And Walter Pitts was a homeless guy, a wannabe logician who just ended up at Warren McCullough's door one day. And McCullough let him stay with him, and the two of them worked together. McCullough must have been very generous, but then it turns out that Pitts was super smart. And so the two of them worked together for several years and came up with the first logic-based model of the human brain. Anybody want to guess which of these two guys is McCullough and which of them is Pitts? Anyone? Super quiet. So this guy with the wine glass is McCullough, and this guy is Pitts, right? And they became really close friends. When McCullough died, Pitts was so heartbroken, he died shortly thereafter. Anyway, here is the model they came up with. I read this paper, and this paper is incomprehensible to me. The math is too complicated. Pitts was not even 20 years old when he produced this math. Mekela was not into math. He was the neuro side of things. But the two of them came up with the model that the functioning of the brain could be expressed in terms of Boolean logic. That was their breakthrough. And so this is how they modeled the individual neuron. A single neuron has two kinds of connections. It has excitatory synapses, shown in green, and inhibitory synapses, shown in red. So the excitatory synapses, each of them get in a certain amount of signal. When the total signal exceeds a threshold, the neuron fires, except if this inhibitory synapse is on. And so if the inhibitory synapse is on, regardless of the remaining outputs, there is no output. And they showed how, using this simple basic unit, you could actually create various Boolean gates. Here, for example, each of these gates over here is going to fire if the total input equals or exceeds 2. Here, anytime neuron 1 fires, one time instant later, neuron 2 gets 2 inputs, so it will fire. So this is just a simple delay. The figure to the right, what do you think this is? Anybody want to tell me what this one is? The figure to the right, what Boolean gate is it? It's an OR. Regardless of whether 1 or 2 fire, this is going to get 2 inputs and this will fire. So this is an OR. What about the one at the bottom? Bottom left. That's an AND, right? Easy. You need both of them to fire for the neuron to get 2 inputs. This one, the one at the bottom right, this is more complex. It's A and not B, 1 and not 2, X and not Y. That's correct. You want X to fire, then it gets 2 inputs, but at the same time, if 2 fires, it will not fire. So 3 will not fire. So it's 1 and not 2. So they showed that you can come up with pretty much any Boolean gate. And they even showed how you can create illusions of perception. There's a very common perceptual hallucination that we all suffer from. If you touch something that's very cold, very briefly, your initial sensation is going to be heat. But if you continue to touch it for a while, you will actually feel the cold. And they came up with a circuit which explained this. So you have cold receptors and heat receptors, and then you have heat sensation and cold sensation. Now, if you have a very brief cold sensation, the first time instant, this signal goes to 4, but it gets only 1 input. So this doesn't fire. And at the second time instant, this is already off. So this is not going to get more than 1 input in any case. So this will not fire. So if you have a very brief touch of cold, the cold sensor actually doesn't fire. On the other hand, if you have a very brief touch of cold, then 1 time instant later, this blue neuron will fire. And then 2 time instants later, this red neuron will fire. And the red neuron will fire because the cold sensation was very brief. So this inhibitory connection is not going to be functioning. And then 3 time instants later, this heat sensor will fire. So if you very briefly touch cold, your initial sensation is going to be heat. But if you keep your finger on the cold, at the second time instant, this will still be firing, but then so will the blue line. And so you will actually feel the cold. But then what about the heat sensor? Because this continues to fire, although this blue will trigger the red connection, this inhibitory connection will stop it from firing. And so the heat sensor will not fire. And so you have a circuit which beautifully captures a well-known phenomenon, that a brief touch of cold gives you a hot sensation rather than cold. But if you continue to sense cold, continue to get a cold stimulus, you will actually sense the cold. So it was a breakthrough. But then they had many claims. They claimed that the net should be able to compute a small class of functions. They correctly claimed that if it had an infinite tape, it would actually be a Turing machine. But they didn't prove any results, and they didn't provide a learning mechanism. They didn't explain how the network could learn to perform its operations. For that, we had to wait for this guy, Donald Hebb. And Donald Hebb was a colorful character. He was a novelist, he was a farmer. At some point, he decided he wanted to be a hobo, so he just took off and became a hobo. And then got bored of it. He went and became a teacher, and then finally went back to Harvard and did a PhD. So we can call him the father of modern neural networks. He wrote this book called Organization of Behavior in 1949, where he said this: when an axon of cell A is near enough to excite a cell B and repeatedly or persistently takes part in firing it, some growth process or metabolic change takes place in one or both cells such that A's efficiency as one of the cells firing B is increased. So it's a very complicated statement, but it basically says that neurons that fire together wire together. This figure explains it better. So let's say I have a neuron X and a neuron Y. These are connected through the dendrite. This is the dendrite of neuron Y. And the neuron X connects to it through this bulb. They don't actually touch. What happens when you have signaling is that some chemical goes down over here, the chemical is released, and that's sensed by the dendrite. Now, every time neuron X successfully makes neuron Y fire, then the size of this head increases, and so the weight of the connection between the two actually gets larger. And so if X repeatedly triggers Y, this bulb called the synaptic knob gets larger, and the weight of the connection increases. So the weight of the connection between two neurons is modified according to this formula. Wxy is incremented by some eta times xy each time both x and y fire together. So this is called Hebbian learning. And it's actually the basis of many learning algorithms in machine learning. And sort of models this notion of neurons that fire together, wire together. So, but what would be a problem with something of this kind? Can anybody tell me? Thank you, Josh. It does not decrease, right? It's fundamentally unstable. Stronger connections will enforce themselves. There's no competition. There's no reduction of weights. So eventually just random coincidental firings will keep increasing the connections till they all saturate, and it will become a useless machine. So there were many corrections, modifications of this model proposed later, including the so-called generalized Hebbian learning or Sanger's rule. There were other modifications, other variations that allowed for weights to be decreased and so on. But then yes, poll 2. So let me release this poll. We'll have, our next poll. And you have 15 seconds, 30 seconds. All right, 5 seconds, guys. Okay, and what is the answer? Perfect. And that is indeed what most of you chose. So it's fundamentally unstable because there's no reduction of weights. Our better model awaited this guy, Frank Rosenblatt, who was a psychologist and a logician in Yale, and the so-called inventor of the solution to everything, also known as the perceptron, in 1958. So he came up with this rather complicated model for a perceptron, or for the neuron. And his neuron was not a simple object, some simple entity. It actually had many subcomponents, and a single neuron that, or single compute unit that Rosenblatt came up with, had this structure where you had many sensory units. These sensory units activated a bunch of so-called association units using some fixed mechanism. And then the outputs of these association units went to response units and the weights. The response units had learnable weights. So each of these response units is what really is of interest. Now, the response unit can be thought of as being something like this. Each response unit gets many inputs. Each input has a weight for its connection. If the weighted sum of all of these inputs, x, which is summation wi xi, exceeds some threshold t, that response will fire. Otherwise, it stays as 0. So this is what is also called threshold logic. And so there was some misconception that was not due to Rosenblatt, who knew what he was working with, but there was a misconception. And the misconception was that this simple threshold unit could represent any Boolean circuit and perform any logic. So, although Rosenblatt claimed that of this larger unit. And so back in 1958, all of the newspapers and such like got very excited, and they came up with these very sort of exaggerated claims. The embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. New York Times, 58. Frankenstein monster designed by Navy that thinks. Oklahoma Times, 1958. So you can see that how the hype was. And the hype led to its downfall. Rosenblatt also gave us a learning algorithm. So he told us how these weights could be learned. And the idea was it's very similar to Hebbian learning, except that there was now, in Hebbian learning, there was no notion of a target. Weights just went up and down depending on whether neurons fired together or not. Here he introduced a notion of a target. So any particular response unit had a target output d of x. There was a current output y in response to any input x. And if the target did not match the current response, then the weight was adjusted. And specifically, you can see that if the output needed to be increased in response to an input, then this goes up. But again, it also matches the sign of the input. If the input is negative, then you want the weight to sort of go down, because then the two negatives will become positive. But then he came up with this little rule and showed that this not only learns the weights, but it's convergent for linearly separable classes. And so with this very simple response unit, again, he showed that you can mimic any Boolean gate. So this, for example, in each of these circuits, you have an input. They have one or more inputs. The number shown on top of any line is the weight of that line. The number within the circle is the threshold that must be matched or exceeded for the neuron to fire. And so this is not quite a proportional controller, Rajdeep. This is a threshold logic unit. There's no notion of proportion here. So what is this gate to the top left? Anyone? That's an AND, right? If both X and Y fire, this is going to fire. What about the one to the bottom? That's an OR. What about this guy to the top right? That's a NOT. If X is 1, then the input is going to be -1. This will not fire. If X is 0, the input is going to be 0. This will fire. So you can mimic any Boolean gate. But the problem is that response unit can never model an XOR. There is no setting for those weights that actually, there was a question. So what is that question? Someone raised a hand. What's the question?
This said no solution for XOR, but XOR can be modeled as A and not B, or B and not A. So we can compose using AND and OR, right?
Correct. So, but the point is a single response unit can never compute an XOR, right?
Yeah.
And so here, for example, if you needed some XOR between, if you wanted this response to be the XOR of, say, 1 and 3, this was not going to be able to do it. And so the idea that this unit was universal in its capacity, kind of fits. And this sort of realization sort of put a damper on research, right? People figured that maybe this machine is not as powerful as it's claimed to be. What we really need, and so things froze for almost a decade. But then, after a while, people realize that once you begin networking these things, then it becomes more powerful. Here, for example, as who was the person who just spoke? What's your name?
Shreyas.
Shreyas. Shreyas just mentioned, if I network multiple of these units, now I can form an XOR. I can have one unit which computes X or Y, the other unit which computes not X or not Y, and then a next level unit which uses the outputs of these two units and adds them, and this is going to give you X, XOR of X and Y. So in this whole computation, the output must now be in stages, in layers. And the outputs of the units in this first layer are not individually relevant. What's relevant is the output of this final unit. And so these guys, because they're not individually relevant, we call them the hidden layer. Once you begin connecting things up in layers in a network of this kind, then suddenly it becomes apparent that you can compose arbitrarily complicated Boolean functions. So for example, this network computes this very ugly function of these 4 Boolean variables. So in cognitive terms, it means you can compute arbitrary Boolean functions over sensory input. And we'll talk more about this in the next class. And so to add to our story so far, neural networks, which began as computational models of the brain, are connectionist machines. They comprise networks of neural units. The McCullough and Pitts model represented neurons as Boolean threshold units. They began modeling the brain as performing logic, and Hebb introduced a learning rule. Neurons that fire together, wire together, but this was unstable. Rosenblatt's perceptron was a variant of the McCullough and Pitt neuron with a provably convergent learning rule, but the individual response units are limited in their capacity, but multi-layer perceptrons can model arbitrarily complex Boolean functions. But then our brain is not Boolean. Our brain, we actually get real inputs, it's continuous valued inputs, and we make non-Boolean inferences and predictions. So how do we extend this whole idea to non-Boolean inputs? Let's go back and look at the perceptron again, but this time with real inputs. All these inputs are real. Once again, the perceptron is going to look at a weighted sum of all of these inputs. If the weighted sum exceeds a threshold, it's going to fire. Otherwise, it will not fire. And so if you look at this, or I can alternately state it like so, I can say that the perceptron considers a weighted sum of the inputs plus a bias term. So basically, the weighted sum plus a bias is what is called an affine function of the inputs. Does anyone know the difference between an affine function and a linear function? Anybody? Intercept. So can you explain that? Exactly. So affine is linear plus some constant. So if I take this thing and if I equate it to 0, that's going to be the equation of a hyperplane. If I didn't have this constant, if I said summation wi xi equals 0, that's the equation of a hyperplane that goes through origin. But if I say summation wi xi plus b equals 0, that's an equation of a hyperplane, but it does not go through the origin. And so an affine function is a linear function plus an offset. And so we can think of this neuron as a unit that operates on an affine function of the inputs. If this affine function is positive, then the output is 1, otherwise it's 0. So you can say that you first compute an affine function of the inputs, and then you put this affine value through a threshold gate, a threshold function which outputs a 1 if its input is positive and 0 otherwise. Did that make sense, guys? Is this clear? Yes, no, I expect a response. Raise your hands if it's okay, good. Those who answered yes are representative. Okay. So what is the difference between linear and affine? Now we know, right? But then once you model it in this manner, then you can also make modifications. You can say that I'm computing an affine function of the inputs and then putting that affine value through any other kind of function. Like say, instead of a threshold activation, I could make it go through a sigmoid, which looks like this. And so now the output is going to be the sigmoid operating on this affine value, the affine function of the inputs. And so this is going to be a different kind of activation function. But anyway, or we can replace this activation function with any kind of function. And we're going to see several others later. For now, I'm going to continue assuming a threshold activation, which produces Boolean outputs, zeros or ones, because that is useful for interpretation. A sigmoid is like a smooth version of a threshold. Instead of a threshold goes directly from 0 to 1, a sigmoid would smoothly swing from 0 to 1 in a continuous manner. So the output of a threshold is either 0 or 1. The output of a sigmoid is some number between 0 and 1. But we can have other activations too, right? So let's go back and consider this one, where the output is positive 1 when the input is positive and 0 otherwise. That actually represents this kind of a function, right? So you're saying that the neuron computes an affine function of the inputs. If it's greater than some threshold, the output is 1, otherwise it's 0. The boundary is exactly where the weighted sum of the inputs is exactly equal to the threshold. This is the equation of a hyperplane. In 2 dimensions, it's the equation of a line. And so the boundary is a hyperplane. For all inputs on one side of the hyperplane, the output is going to be 1. For all inputs on the other side, it's going to be 0. So for a 2-dimensional input, if I were to draw this in 3D, the function is going to look something like this. There's a boundary plane. On one side, the output is 1. On the other side, the output is 0. Is this making sense, guys? Any questions? Okay. And so once I can do this, you can see how the Boolean functions came to be, right? If my inputs were Boolean, if I had 2 inputs, the inputs could be either 0, 0, 0, 1, 1, 0, or 1, 1. And if I had a perceptron which had this decision boundary, what Boolean function is this perceptron computing? Anyone? That's an OR, right? What about this guy? I just shifted the boundary over to this side. What does it compute? That's an AND. And this one is only, it's ignoring x2, it's only responding to x1, and it's computing not x1, right? So simply by, and William, can you tell me why you cannot compute an XOR from looking at this figure? Anybody? We will need 2 boundaries, right? For XOR, the output has to be 1 in both these corners, and in these 2 corners, the output has to be 0 for these 2 corners and 1 for these 2 corners, which means you want the output to go up and then come back down. And a linear boundary cannot capture that. That's why you cannot do an XOR with a single unit. But then once I begin assuming that I can connect these things up, here are more complicated things I can do. I can compute this boundary. I can compute a network which has an output of 1 if the input lies within the pentagon and 0 otherwise. How do I do it? I first have 1 unit which captures this boundary. The output of this unit is 0 if the input is in the white region and 1 if it's in the yellow region. Another perceptron for this one. A third perceptron for this boundary. A fourth one for this boundary. A fifth one for this boundary. And then I can add a next layer perceptron which only fires if all 5 of these inputs are 1. The way it would do it is it's just going to have weights of 1. It sums all the outputs, and the sum is going to be 5 only within the pentagon. I can use a threshold of 5, and so this neuron will fire if the total input is at least 5, which means it will only fire if the input lies within this pentagon. And so now I'm able to compose a pentagonal decision boundary. But once I can model a pentagonal decision boundary, I can do something more complex, like this guy, right? This is a double pentagon. I want my network to fire if the input lies within either of these pentagons and not otherwise. Easy. How do I do it? I have one subnetwork which fires if the input is in the lower pentagon. I have another subnet which fires if the input is in the upper pentagon. And this final one is simply going to OR these two. It's going to fire if it's either this one fires or if this one fires. And voila, I actually now have a network which captures this double pentagon decision boundary. But then once I can capture a double pentagon decision boundary of this kind, I know exactly how to compose more complex decision boundaries like these. How do I do that? Anyone? Many layers, deeper networks. I let you think about it, right? What I could do is I could fragment this guy into many little pentagons, right? Break them into polygons. Perfect, Josh. And then I can just OR the lot. And so I can compose, just as I composed a double pentagon, this guy is the union of many pentagons. So is this guy, or polygons. And I can compose them into, no, I don't need a nonlinearity. It's just this, right? Literally the same trick. We'll see this again in the next class. And so we can, now when I begin looking at classification boundaries problems, it's all about finding decision boundaries in high dimensional spaces. For example, if I want to look at images such as this, and I want to decide if this is an image of the digit 2 or not, this is a 784 pixel image. So this lives in some 784 dimensional space. In that 784 dimensional space, there's some region of the space which represents instances of the digit 2. Anything outside that region is not the digit 2. And so all I need to do is to compose a neural network which captures this decision boundary. And the way I would do it is just like so, right? I can decompose that region into the union of many polygons and then combine the lot. So MLPs can classify real value inputs with arbitrarily complex decision boundaries. And so our story so far, MLPs are connectionist computational models. Individual perceptrons are equivalents of neurons. The MLP, what is this MLP? It's a multi-layer perceptron. I forgot to mention this this terminology earlier. When I begin connecting networks of these neurons in many layers, we call it a multi-layer perceptron. It's a layered composition of many perceptrons. They can model Boolean functions, as we saw. Networks of perceptrons are Boolean functions, but they're Boolean machines. They can represent Boolean functions over linear boundaries. They can represent arbitrary decision boundaries. So they can be used to classify data. And so we have our third poll. Let me release poll 3. The threshold is a nonlinearity emblem. Right? All we did was if you have an arbitrarily complex decision boundary, you can just break it down into many polygons, right? The combination of many polygons. Can you not? Or polytopes. And so when I have it as a union of many polytopes, I can pretty much compose any boundary. 5 seconds, guys. Okay, does anybody want to answer this question? 7, right? That's correct. So the correct answer is 7. You want to have a hexagon, and so you will need 1 neuron each for each of the 6 sides, and the final neuron on the outside to OR the lot. Beautiful. Now, but what about continuous valued functions? The inputs may be real valued, but we saw Boolean functions, right? Can the outputs be continuous valued? And the answer is yes. Here's how. Consider this, guys. I may just go a few minutes over because we lost time to almost 10 minutes to Everly. So consider the simple function of a single input. So this input is going through 2 neurons. The first one fires if the input exceeds a threshold of T1. The second one fires if the input exceeds a threshold of T2. Their outputs are being combined with weights 1 and -1. And there's no additional threshold activation beyond this. So if you look at what happens, assuming that T1 is lesser than T2, as the input increases, when it exceeds T1, this neuron will fire, but this will not. And so the total output is going to be 1. But as the input continues to increase and it exceeds T2, this neuron will also fire. And so now this neuron's weight is -1. So the sum of the 2 of them are going to combine, and the sum is going to become 0. And so the overall output is going to go back to 0. And so this circuit will produce an output of this kind, which has a value 1 between thresholds T1 and T2 and 0 outside. Is this making sense? This figure? Yeah. And so now, if I want to model a very complicated decision boundary of this kind, a very complicated function of this kind, it's easy enough. I'm going to sort of decompose the range, the domain, into many little intervals. And within for each interval, I can have 1 pair of neurons creating a little square pulse there. And then I can scale that pulse up by the height of the function within that domain, or within that little interval. And so I can approximate this blue curve by the sum of all of these little rectangles. And so now I can model this blue function to arbitrary precision. It's not going to be perfect, but it's going to, but you give me an error tolerance, and I can always may create a network which will model it to within that tolerance by making these intervals narrower. Is this making sense? Yeah, right. So, and so here is your 4th and final poll for the day. You have 30 seconds. And actually stop this. This was a bit of a trick question. It's out of left field, but does anybody want to take a shot at the answer? Infinite. So when I say, instead of if I replace the threshold by activation and by sinusoid as an activation, then in fact I only need 1 neuron, right? Because if I want y equals cos x, that's y equals sine of 2x plus pi over 2. And so all I would do over here is I'd have a single input. This weight would be 2. This would be pi over 2. This function is sine, and so you're going to end up with y equals cos x. Yep, exactly, Dennis. Perfect. And so, anyway, coming to the end of this class, what we've seen is multi-layer perceptrons are connectionist computational models. They're classification engines. They can identify classes in the data. Individual perceptrons, I'm calling them feature detectors. We'll see that why this is the case later. but they detect whether individual boundaries in the class, in the space. And if the combination of the detected boundaries matches an acceptable boundary, then it's going to fire. We also saw that the weight would be 2. So I have a single weight. I have the input X. The weight is going to be 2, and the bias is going to be pi over 2. Right? So, did I answer your question, Advait? Okay. So, MLPs can do all kinds of things, as we see. And you can even model memory. If you add loops, then you can make them remember patterns. We'll talk about this much later in the class. They can generate probability distributions over integer, real, and complex value domains. They can model both a posteriori and a priori distributions of the data. We'll talk about how they model a posteriori distributions in the next several lectures, but later on we'll talk about, much later in the class, how they can model the actual distribution of the data themselves. They can generate data from complicated or even unknown distributions. And I just like to have this, it's facetious. But anytime you see people doing something strange, it's probably an Indian, right? They actually have competitions for whether you can rub your stomach and pat your head at the same time. And Indians win. But yes, I like to joke that something as complicated as that can also be done by neural networks. Anyway, so going back, the neural network is a function. That's what we found. Given an input, it computes the function layer-wise to predict an output. Or more generally, given one or more inputs, it predicts one or more outputs. And so all of these tasks are, each of the boxes in each of these cases is actually a function. So it's the speech recognition system is a function that takes in a voice signal and produces a transcription. The captioning system is a function that takes in an input and produces the caption. The game playing system is a function that takes in a game state and predicts the next game state, and so on. And because these are functions, these can be approximated by a neural network. And so to close our lesson, interesting AI tasks are functions. And because neural networks can model Boolean functions, they can model any classification boundary, and they can model continuous valued functions. AI tasks, which are functions, can be modeled by neural networks. And so for the lessons of the day, we've seen a brief history of neural networks and connectionism, early models and their limitations. We introduced model neural networks, modern neural networks, and saw what they could compute. And in the next lecture, we'll see more on why they are universal approximators and discuss the importance of depth in networks. I'll stop right here, right on time. But if you have any questions, I'll take questions. Any questions? I'm assuming not, so let me stop the recording.